Electrokinetic remediation of soil. Let's talk about EKR, but before we get into it, let's observe how contaminants are all around us. Here's a conceptual site model showing how direct exposure can impact humans and animals, and it can indirectly impact our water habits and our air quality. Now that we know it's all around us, what are these contaminants? Common soil contaminants include pharmaceutical products, petroleum and hydrocarbon products, heavy metals, and pesticides. These contaminants can arise from a variety of manufacturing processes. These can include construction, transportation, and even agriculture. What is EKR? Electrokinetic remediation is the use of an electric field to attract contaminants such as heavy metals, radionuclides, and organic compounds to the electrodes. Through the attraction, contaminants are removed from the soil. Here we will give a brief overview of key processes in EKR. These processes include electromigration, which is the movement of ions based on charge, electroosmosis, and electrophoresis, which is the movement of ions through a specific medium. These will be looked at more in depth in advanced slides. So, how do we know if EKR is suitable for a contaminated property? The suitability of EKR depends on ionic mobility, contaminant solubility, soil type, charge, and the chemical and physical properties of the contaminant. EKR is highly suitable for low permeability soils like clay and silt, with a pH of 4 to 7 and a high ionic solubility of the contaminants.
So to begin the EKR process, a contaminated site is first assessed in order to determine the placement of boreholes and wells. Then electrodes that are commonly made out of materials like graphite, platinum, and silver are inserted either directly into the soil or within wells that are filled with an electrolyte to boost the flow of charged particles. Once connected to a power source, a low-level direct current creates an electrical field that is used to push ions from the positively charged anode to the negatively charged cathode. And it's this electrical field that enables three key mechanisms to move contaminants through the soil. So the first key mechanism is called electromigration, and this involves when ions move towards the electrode of the opposite charge. Cations that are positively charged, like copper and lead, move towards the cathode and negatively charged electrodes, while ions like nitrate and chloride move towards the positively charged electrodes known as the anode. The next process is electroosmosis, and this is when the electrical field drives water flow, usually from the anode to the cathode, which can carry dissolved contaminants along with it. The next one is called electrophoresis, and this is when charged particles are suspended in water and move through the soil, driven by their surface charges and the electrical field, towards the electrode with an opposite charge. This works particularly well when mobilizing fine contaminant particles. There are other additional forces included in this process, like advection, where water moves from high to low pressures, and diffusion, which is the movement from high to low concentrations, which further aid in contaminant transport. However, one of the most crucial reactions here is the electrolysis of water, which splits water molecules into hydrogen ions at the anode and hydroxide ions at the cathode. This reaction is what creates an acid front at the anode, altering the pH levels, making the area near the anode more acidic and the area near the cathode more basic. This acid front is what's used to help mobilize certain contaminants for extraction. Now, throughout the process, monitoring is crucial, as you can see in this picture. Factors like voltage, current, and water flow are adjusted to optimize contaminant migration. However, the success of EKR is largely dependent on site-specific variables, such as the soil type, the pH, and the nature of the contaminant.
So the two main contaminant problems that are solved by electrokinetic remediation are inorganic contamination and organic contamination of soil. So, inorganic contaminants can be things like heavy metals, which can cause multiple organ system damage and bioaccumulation if they come into contact with humans or animals. And organic contamination can cause toxicity and can also bioaccumulate. So, this is why these are problems. And electrokinetic remediation has been shown to remove a variety of heavy metals, like up to 85% of zinc, up to 85.5% of copper, and over 90% of nickel. And it is even able to remove emerging organic compounds, which a lot of treatments have problems with. So that's 75 to 83% of antibiotics and also 58.6% of another organic contaminant, which is called PCBs. And a major problem also solved by electrokinetic remediation is that it can work well in low permeability soils like silt and clay. So other treatment types don't work well in these types of soils because the treatment can't come into contact with the contaminant. But since EKR, as we mentioned, works with the electrochemical gradient, it works very well in these conditions. So we know that EKR can be an effective remedial technology, but from the client's perspective, cost is one of the most important factors to consider. So from our economic analysis, we showed that the average capital cost is 553.5 Canadian dollars per meter squared. The operating cost is 406.3 Canadian per meter squared, and the total treatment cost is around 589 Canadian dollars per meter squared. So this is based on four different sources that we were able to find. And as you can see on the right, EKR is on average more expensive than other treatment technologies. So all the advantages and this limitation have to be considered altogether.
There are a variety of remedial methods available and each has context-dependent advantages and limitations. Here we will compare electrokinetic remediation with other some common remedial technologies. If we compare electrokinetic remediation with bioremediation, we can see that electrokinetic is very effective in low permeability soil compared to bioremediation. If we compare electrokinetic with phytoremediation, and both are green technology, but electrokinetic is a faster compared to phytoremediation. If we compare electrokinetic with an ex situ technology like soil washing, we can see that it is very electrokinetic is very non-invasive and preserves soil structure, which is very important for the sustainable environment. And for soil washing, it is very disruptive to environment and also expensive. Based on efficiency, we can combine electrokinetic remediation with some other remedial technologies like bioremediation, phytoremediation, so that they provide maximized they provide maximized remedial results. Advantages of electrokinetic remediation. Electrokinetic remediation is very effective in low permeability soil like silt and clay, and they are minimal disruptive to environment. It is also a flexible technology because it can remediate metal, organic, and inorganic contaminants. Electrokinetic remediation is a very cost-effective and rapid contaminants removal. That's why it is very appealing to stakeholders also. Everything has some negative impacts. In our case, electrokinetics has some challenges. Like first, electrokinetic is ineffective against non-ionic contaminants like hydrocarbons. Second, in acidic conditions, electrokinetic shows limited performance because there is a chance to corrosion of electrodes. Third, hydrolysis of water is an essential reaction in electrokinetics. So there is a chance that electrokinetics dependent on moisture content. Fourth, during electrokinetics reaction, it may cause changes in contaminant media. That's why it may help to develop secondary byproducts like chlorine. Fifth, Sometimes light or dense non-aqueous phase liquids may obstruct electrokinetic reaction, which makes a site unsuitable. Finally, before applying electrokinetic remedial technology, we have to consider soil and contaminants types.
So for EKR to become more mainstreaming, there are some market barriers that we need to overcome. But first, let's briefly recap the advantages of EKR that much have been just discussed. Effective in low permeability soil, it has minimal environmental disruption, it's a very flexible technology. It can rapid remove contaminants from the soil, and it's overall a very appealing technology to the stakeholders. And these points underscore why EKR is not just a promising technology, but also a practical solution for our environmental challenges nowadays. And understanding these benefits help us to appreciate the potential barriers to its wider adoption, which we will discuss in the following slides. And despite its potential, EKR faces significant market barriers. The high initial and operational costs sometimes can make it a tough sell, especially when the customer have a very tight budget, and I believe that's always the case. And the very strict regulatory landscape and the scarcity of demonstrated successes will make stakeholders hesitate a little. And let's dive into those challenges and consider how can we overcome them. Innovation in technology can provide a pathway to overcoming market barriers by developing cost-effective materials and integrating sustainable energy sources. We can make EKR both economically viable and environment friendly. Also, advances in monitoring technology also allow for more precise and efficient contaminant removal. For EKR to become more mainstream, strategic initiatives are very important. Cost management will make technology more accessible, while the ongoing research and development will broaden its applicability. Also, engaging with regulator will help establish EKR as a safe and effective solution, paving the way for a wider acceptance and application.
Let's review what we've learned. EKR is particularly effective for in situ treatment of fine-grained, low-permeability soils, minimizing site disruption. Soil types include clay and silt. EKR is complementary with other remediation techniques and can be paired to increase overall efficiency. High costs associated with energy, operational costs, regulatory frameworks, and gaps in research hinder mainstream adoption. With strategic investment in technology and regulatory collaboration, EKR can overcome current barriers and become a #1 green technique for remediation. Thank you.